All right, let's peel back the curtain on artificial intelligence and get to something really fundamental. How does an AI actually solve a problem? I'll give you a hint. It's not magic, it's a method. And it's a powerful, systematic way of thinking that we can totally understand by turning any problem into a kind of map. Okay, let's get into it.
I mean, think about it. When you're faced with a tough puzzle, what do? You probably use your intuition, right? You have a flash of insight, maybe try a little trial and error. You kind of feel your way to the solution. But what if there were millions of possibilities? An AI can't just wing it. It needs a much more structured approach.
And that, right there, is the big idea for today. An AI takes a complex, messy problem and transforms it into a clean, logical map. A map where your starting point is the problem, the destination is the solution, and the AI's job? It's just to find the best path from A to B.
This whole concept is called search, and believe me, it is everywhere. When your GPS finds the fastest route to a restaurant, it's searching a map of roads. When a self-driving car is planning its next move, it's searching through all the possible futures. Even an AI that plays chess is just searching for the best sequence of moves on a giant map of all possible board positions.
So to really see this in action, we're not going to tackle self-driving cars just yet. We're going to use a classic, simple little puzzle. A robot needs to get a fox, a chicken, and a bag of chicken feed across a river. Trust me, this little brain teaser is the perfect way to build our map and really start thinking like a machine.
Okay, so every problem has rules, and these are our constraints. The robot is the only one who can drive the boat. The boat has a limited capacity, and most importantly, we have these two disastrous outcomes we have to avoid at all costs. The fox cannot be left alone with the chicken, and the chicken cannot be left alone with the feed. These rules, they define the boundaries of our map.
Now, a person might just start guessing moves. Let's try moving this, then that. But an AI doesn't guess. Its very first step is to methodically, almost robotically, list every single possible situation, we'll call it a state, that could ever exist in this puzzle. It doesn't matter if it's a good situation or a bad one, it lists everything. So how does it actually do this? Well, it just simplifies reality. We've got 4 items: the robot, the fox, the chicken, and the feed. And each one can be in one of only 2 places, near or far. If you do the math, that gives us exactly 16 possible combinations. We can just label them, like NNNN means everyone's on the near side, and FFFF means everyone's on the far side. This right here is our complete theoretical universe of possibilities. But hang on. Remember those rules? The ones about who eats whom? The AI now takes those rules and uses them like a filter. It goes through every single one of those 16 states and asks a very simple question. In this configuration, does something get eaten?
And here's how that filtering process works. Let's take state NFFN. So the robot is on the near side, but the fox and the chicken are alone together on the far side. Uh-oh, that's a forbidden state. The fox eats the chicken, so the AI flags it, throws it out. It does this for every single combination, just mechanically checking against the rules. And after it eliminates all 6 of those danger states, we're left with just 10 valid safe ones. This is our final map. These are the only places our robot is allowed to go.
You know, now that all the hard work of actually building the map is done, the problem gets a whole lot simpler. All the AI has to do is find a sequence of moves that connects our starting state, NNNN, to our goal state, FFFF, by only stepping on those 10 valid dots on our map. It's really just a pathfinding problem now.
And here is a solution it finds. So, trip 1. The robot takes the fox and chicken across, leaving the feed behind. Safe. Now look at trip 2. The robot brings the chicken back to the near side. Now that might seem totally counterintuitive, right? Why would you go backwards? Because the AI has mapped out all the possibilities. It knows that moving forward would lead to a dead end, or worse, a forbidden state. By returning the chicken, it opens up a new, safe path that allows it to make that final winning move, taking the chicken and feed across, and finally solving the puzzle. Okay, so we solved the puzzle. Great. But way more importantly, we've just used the core concepts that AI researchers use every single day. So let's put some official names to the tools we just played with. First up, we have the state space. That's our map. It's the complete set of all the valid situations, or nodes, in a problem. For our little puzzle, the state space was simply those 10 safe configurations, from everyone being near to everyone being far. Next up, transitions. Think of these as the lines that connect the dots on our map. A transition is just a single legal action that takes you from one state to another. For us, every boat trip across the river was one single transition. And finally, we have costs. Now, while every trip in our puzzle was basically equal, that's almost never true in the real world. A transition can have a cost, like time, or fuel, or distance. And AI uses these costs to find not just any path to the solution, but the most efficient one, the cheapest path. So you might be thinking, okay, that's a cute little puzzle, but how does this possibly relate to something like a self-driving car? Well, the incredible thing is, the fundamental logic is exactly the same. It just operates on a scale that is almost impossible to imagine. And this is where it all clicks. Our little puzzle had a state space of just 10 nodes. A self-driving car state space, it includes billions of possible positions for itself and every other car, pedestrian, and traffic light on the road. Our transition was a boat trip. Its transition is a tiny turn of the steering wheel. The scale is astronomically different, but the fundamental logic of mapping states and finding a path, it scales perfectly.
And that is the real takeaway here. Our human brains are incredible at finding clever shortcuts, but we get totally overwhelmed when the possibilities just explode into the millions. This systematic, mechanical approach of defining states and transitions and searching for a path, that's what allows a computer to navigate a level of complexity that is just way beyond our own mental capacity. It doesn't have a gut feeling, it has the map.
So the next time you find yourself stuck on a problem, maybe try swapping your intuition for a map, just for a minute. Ask yourself, what are all the possible states? What are the valid moves? And what's the path from where I am now to my goal? You might be surprised to find that the most elegant solution isn't some flash of genius, but just the best path forward.